of all, let's get straight into it. What is congestion control? Well, congestion control is essentially a way to manage and mitigate the loss of packets throughout a network. So given the, say you have traffic that you're pushing through your network and you're pushing so much at a time that your bandwidth resources are depleted because of that. Now, the congestion control is just a means to as it says, control that functionality. And it's controlled by the network and transport protocols, and there's various different control laws that manage congestion in the network. And there are three types to the elements of congestion control, which is the efficiency and power, which relates to how effective you can utilize your resources in the network to the best of their ability, and power, which power is essentially just a synonym for whether you're using everything to the fullest, and that is denoted by the formula of load over delay. Load is how much the bandwidth can support, and then the delay is the wait time between each packet send. And the max-min fairness is essentially allocating resources based on priority. So if I have one specific connection that needs more than another, we want to make sure that the amount of bandwidth that is given to that is appropriate so that it doesn't consume some of the other resources of the other one. And then convergence is to make sure that all those come together at once. So we get to what is known as the AIMD, which is the additive increase multiplicative decrease control law, which basically states it's essentially a way of mitigating that kind of oscillation of congestion and then freeness of resources in the network. And as you can see from the graph here, what it does is when it starts to go towards the latency portion, it'll bottle it back down to a more usable field. So it's more or less a balance. So also this leads to the problem of wireless issues. So if in a normal wired network, you have a latency, usually your latency is about 1%. And when you get into a wireless network, because there's so many different variables to that, you can have a packet loss of up to 10%, which is usually common for those. So how do you fix that? Well, you basically have to bridge that gap between your packet loss and then increasing your bandwidth. And one way to do that is use what is known as the masking scheme, which essentially uses a wired and wireless link to kind of bring that latency down to a more sophisticated level. And we have a video that we're going to show you.
If we need it to work.
By the networking. Let's compare this. So in UDP, the sending computer does not establish the session first. It just starts sending data. Here's data set 1, here's data set 2, here's data set 3. Again, let's say data set 2 goes missing for whatever reason. What will happen next is the sending computer will send data set 4, data set 5, data set 6. In the transport layer protocol, there is no built-in mechanism to resend lost packets. UDP is great if it's okay to be missing some data. Video conferencing is a great example. Let's say dataset 2 represented second 2 in a video conference. By the time that TCP would realize that dataset 2 is missing and the sending computer resent that packet, we would already be several seconds down in the conversation. So taking that second of the video conference and replaying it 5 or 6 seconds later would be completely inappropriate. So UDP with the lower overhead, there's not all the overhead of the sessions process, is much more efficient. So it's better for something like video conferencing. Usually we care about the data. We need all of the data. So TCP is the preferable choice. Web pages are a great example. If it takes 3 data sets to transmit a web page to your computer, you can't have one of the data sets missing and still be able to render the page.
So that was kind of a brief little overview for the UDP. I'm going to hand it over to Josh, and he's going to talk about UDP in more detail.
Yeah, so UDP, it's the user datagram protocol. It is a transport layer protocol, and it is connectionless, meaning that it doesn't go through the whole handshake thing that TCP goes through, and like there's no real guaranteed delivery. You just kind of send the stuff out and hope that it gets there. Yeah, provides means for sending the packets without an established connection. The UDP header consists of a source port, which is an optional port for if you are expecting to receive data. You'll put your own port in there and then send it out and hope you get something back. The destination port is, of course, the port of the destination computer or whatever. UDP length holds the length of the header, and the checksum is an optional thing in IPv6 that uses a one's complement to compute a checksum to make sure that nothing's missing. Segments are sent without previous connection attempts, so it's like sticking a letter into a mailbox. You know, the post office is probably going to get it there, but it might not. And like the video said, missing segments are not resent because usually by the time that you need it, it's either past the time that it's useful or it's just something that you can just resend the acknowledgement or the request for. There's not a lot to UDP. It's a pretty simple, straightforward protocol. Just kind of send the stuff out, hope it gets there. Probably don't need anything in return. So I'm going to hand it off to Morgan, and he's going to go over RPC.
All right. So RPC, as you can see on there, is remote procedure call. This pretty much lets one program or a procedure or subroutine in one address space or computer to be called from another address space. Usually over a shared network at work or something like that. So it operates on request-response basis, and the procedure actually goes like, so this is the client, it calls the client stub, this is the client stub, which is a local program that has a set of parameters and pretty much information it needs to collect. It goes through a marshalling process, which really just is a fancy name for gathering it all in and putting it into a special message. It sends it to the operating system with a system call, and then the operating system, sends it across the network to the server's operating system, which then does the entire thing backwards. It takes it, puts it into the server stub unmarshals the packet information, and then the server uses the information as you would as if it was already on the client. And then it sends the response back the same way. So this is all done without sockets because it's all localized, and so with the way it happens, it just doesn't need sockets. And then while this process is happening, the actual process on the client is suspended until it receives the response so that it doesn't get ahead of itself or lose any important data. Now, all this is good, but there are a few drawbacks. Pointers are always required for this, and because they're on two separate systems, you can't just use the pointer from the client on the server or the server on the client. So to do this, they fixed it by where the marshalling service actually takes the value from the relevant pointers and sends that value in with the marshalling message. And then the server takes, after it unmarshals it, creates new pointers and assigns those values to the relevant pointers and does the same thing backwards when it's sending its response. And so it pretty much just modifies the already set procedure. Then, as you see here, data types are not always there. They're sometimes lost. That can be an issue. In languages like C, there are some times when you can't figure out how large an array is, and that just makes the entire marshalling process impossible. So you can't do that. So, And obviously, because it's on separate computers or memory spaces, global variables are lost. So with that, I hand